My name is Fernando Meneses. This talk I'm going to talk about combining quantum diamond sensing with a machine learning application to solve a real-world problem. So I will explain first the outline of the talk, in which I will describe you briefly the context that we have, the problem and the objective that we've set, then the methodology that we are employing, the results, and finally the conclusions. So let me begin with the context. What we want to do with our magnetic sensing technology is to track in real time an object, which is a task normally done by very well-known techniques such as GPS. But there are certain cases in which we cannot apply that technique, such as in closed environment as indoors, underground, or underwater. So in that cases, magnetic sensing can be especially useful. But even if we have that technology, most of the times the object under tracking or the system in which it lives is very complex. So we need very complicated physical models or simulations in order to reproduce the experimental results or understand what's happening. And many times that's not feasible. So what we would like to do is to develop a method that relies in experimental data, that only measuring the data and then predicting the position of the target. So that brings me to the problem that we identified, that in the situation of an enclosed environment in which we need magnetic sensing, that we want to track in real-time magnetic object, to our knowledge, there is no method that relies exclusively on experimental data. So what we want to do is to develop a machine learning algorithm that will be exclusively trained with experimental data. So let me introduce the system that we are tracking, because the objective is very general, but we are going to focus on an elevator, which is in our School of Physics building. And this is a magnetic system. Our objective is the magnetic car. But this is not the only element in the system. We also have the counterweight that has a magnetic signal, the steel cables, and the electrical motor on top. And to make it a real-world problem, we have our environmental noise, which is coming from distant electrical trams. So this is a complex system, all in all, within a noisy environment. And we don't know any of the magnetic information of the elements. So what we want to do with our machine learning is ignore all of this. We don't need any of the magnetic information, but we do need some information about the elevator itself, which is very easy to measure. And we know that the elevator can travel between level 1 and level 8, that levels are spaced 4 meters apart, that the average traveling speed is 1.4 meters per second. So it takes more or less 3 seconds to go from one level to the next one. And that sets our time scale. So given all this situation, we've established our goal, which is using this machine learning algorithm. And because we want to predict in real time the trajectory of the lift, considering this 3 seconds time scale, we've chosen a time resolution of 0.1 seconds. And we want to have an 80% accuracy within 1 meter tolerance, which I will explain in this scheme. Here you can see the elevator going from level 2 to level 3 as a function of time. And I'm talking about 1 meter tolerance, but you may think that the elevator is a bulky object. It's 2 meters high. But in fact, the elevator will only open its doors when it is aligned with each level. So what we are really tracking is a single point in the lift. You can think that we are tracking the bottom of the lift. So this 1 meter tolerance refers to that target position. And to define the accuracy, I will introduce two concepts. One is the successful prediction or not. So for each prediction that the machine learning makes, we will consider it successful if the predicted value and the difference within the true value of the position is smaller than the tolerance. So once the machine learning is trained with the entire training data set, we will count all the number of correct predictions divided by the total number of predictions, and that's the accuracy of the model. So when I ask for 80% accuracy, in 1 second, we will have 10 measurements. So that means that in average, 8 out of 10 points will be correct every second, which will be more than enough to reconstruct the trajectory of the lift, even if some points are off the real movement. So considering this goal, we've asked the AI what it wants to do with quantum diamond sensing and this tracking application, and this is the answer that we get, which is pretty nice. But now we will focus on what happened really in the research. So let me begin with the setup that we have. Next to the elevator system is our lab, which is located 10 meters away from the elevator's doors. And we have our magnetometer there. I will explain the details in the next slide. But for now, just take into account that the main features are that it can measure the full magnetic field, Bx, By, Bz, with a sensitivity of 350 to 500 picotesla per square root hertz, which is very good compared to the floor noise in the order of 100 to 200 nanotesla. And we also know that the magnetic signals are below 1 microtesla. So when the lift changes from level to level, the change in the signal is in the order of the floor noise, a few hundred of nanotesla. So let me explain you some few details about the quantum diamond sensor. This is based on an ensemble of nitrogen vacancy defects, which are quantum systems with spin 1. And the very important thing is that they are very sensitive to the external magnetic fields. Because we are using a single crystal, there are 4 possible orientations for the MB defects along the crystal axis. And each of these orientations will be very sensitive to the projection of the magnetic field along that axis. So if we know each of the magnetic projections in this axis, we can reconstruct the full magnetic field. And this is what we measured in the optically detected magnetic resonance. We measured these energy transitions. And here you can see 8 peaks. But in fact, we are having 4 pairs of peaks. And each pair of peaks is split symmetrically based on the intensity of the magnetic fields. So given these energy transitions, we can infer which is the magnetic projection on each axis and then reconstruct the full magnetic vector. So this is our principle of measurements that we will use. And based on that, we will measure the whole signal of the system, our target, which is the magnetic, the elevator car, but also the other elements and the environmental noise. And at the same time, to have the ground truth of the system, what is really happening with the elevator, we will use a camera that is filming the display that tells us if the lift is parked at any level or it is traveling. So this is how a typical record looks like. We have the lift moving between levels. And at the same time, we are recording the magnetic information in Bx, By, Bz. So there is some correlation between them, position and magnetic fields, but the details are not very clear. So what we want to do is to develop this machine learning algorithm that will not use any physical models nor simulations. It will just use experimental data. It will be supervised learning, and the input will be the magnetic fields, and the output will be the position of the lift. So how does it work, this supervised learning? For a short period of time, we have to train the model first. So in order to do that, we have to supply it with predictors, which are the magnetic signals, and targets, the position of the lift. We feed all that to the machine learning model. Inside this machine learning model has an architecture, which we have optimized. It is a collection of convolutional layers and then dense connections that can predict one position at a time. However, you don't need to look into the details. For this application, you can just think that the machine learning model is a black box with an internal structure, and given magnetic predictors, it can predict the position of the lift. So this is a simple cycle in the training stage. At the end of every cycle, the machine learning algorithm will compare the predictions with the ground truth, and it will tune its internal parameters to make better predictions for the next cycle. So this is how the machine learning learns, and after it is trained, we can use it to predict new data without any reference of a magnetic position, of the position of the lift. So here is a new data set, unseen, for the machine learning network. This is a 2 hours recording of Bx, By, Bz. And what we want to do is to predict the lift position. So we feed this data into the machine learning algorithm, and we get predictions for the movement. So let me zoom in these predictions. You can see the horizontal lines there are the parking levels of the lift. So the predictions make sense. They say that the lift is traveling from level to level. And if we compare this with the ground truth,
you have 30 more seconds.
Okay, we have 90% accuracy. So we are, very happy with the results. Of course, there are some weaknesses in the model, but we can reliably trace the trajectory of the lift. So going back to the model, to the goal, in which we wanted 80% accuracy, we are getting 90% accuracy within this 1 meter tolerance. So with that, I will end. So I will thank you all for listening, and any comments or questions are very welcome.
Thank you very much, Fernando, for the interesting talk. Because of the time constraint, we are unable to take some discussions. We'll be discussing in the Gather Town again.
Okay, thank you very much.